2.1 Differentiability. The objective is to understand the relationship between differentiability and continuity. And our definition of differentiability is that the limit exists. So when we look at functions graphically, we need to see that if a function is not continuous at a certain point at x equals c, then it is not differentiable. So let's review the situations in which a graph is not continuous. Remember, a graph is not continuous when there is a hole. So if you have a graph and there's a hole, it's not continuous at this x equals c, therefore it's not differentiable. The second situation in which a graph is not continuous is when there's a break. If we have a break, your graph looks something like this, such as in a piecewise function. So if your graph is not continuous at c, then it is not differentiable. And the third situation is when you have an asymptote. So you'll have a graph has an asymptote at c, so it is not differentiable at c. We can also use the existence of a derivative to prove that a function is continuous. Theorem 2.1 states that if a function is differentiable at x equals c, then it is continuous at c. And in order for us to do that, we need to use the alternative form of the derivative, which is f prime of c is equal to the limit of f of x minus f of c all over x minus c as x approaches c. Okay, and we use this to analyze if a function is continuous and in an analytical way. So we can do it graphically and we can also do it analytically. However, there are situations where a graph is continuous but not differentiable. And those are when we have a sharp turn and when you have a vertical tangent line. Let me show you the first one first. If I had the function f of x equals x minus 2, my function looks like this. I have a sharp turn, a vertex at 2. It's an absolute value function. Now I'm going to prove it analytically that it's not differentiable at 2 using the alternate form of the derivative. So I'm going to use the limit of f of x minus f of c all over x minus c as x approaches c. And in this case, it's not differentiable at 2, so c equals 2. I'm going to prove it at that point. So I'm going to use the limit as x approaches 2 of f of x minus f of 2 over x minus 2. So I have the limit of f of x is x minus 2, minus f of c, which is going to be 0, over x minus 2, as x approaches 2. And I need to do it both from the left and the right side, my left and right hand limits. Okay, because that's one of the requirement is that the left-handed limit and the right-handed limit must be equal. So if I take a look at the left-handed limit as x approaches 2 from the left of x minus 2 absolute value of x minus 2 over x minus 2. And I need to look at the limit as x approaches 2 from the right of the absolute value of x minus 2 divided by x minus 2. If I make a table approaching 2 from the left, well, that's something like 1.999, and we will see that it approaches -1. And if I do it from the right hand side, well, that's something like 2.001, and that's 0.999. So we see that it approaches +1. And so because the left-handed limit and the right-handed limit are not equal, therefore it is not differentiable. My function f of x equals the absolute value of x minus 2 is not differentiable at 2. And now in a second situation, when I have a vertical tangent line, I'm going to show you why it is not differentiable at a vertical tangent line. For example, if I had the function f of x equals x to the 1/3, well, that's the cube root of x, and the cube root function looks like this. Okay, so I'm going to prove that it is not differentiable at x equals 0. It is continuous, but is not differentiable, and I'll show you why in an analytical way using the alternative form of my limit. So my alternative form, we will see that the limit of f of x minus f of c over x minus c, this is the alternative form as x approaches c. If I plug it into my situation here, I get the limit of x to the 1/3 minus f of 0 over x minus 0 as x approaches c, which is just going to be the limit as x approaches 0. And then I'll just get, well, let's see, f of 0 is going to be 0, because 0 to the 1/3 power is 0. So I'm just going to have x to the 1/3 over x. Okay, and in this situation, I cannot use direct substitution, so I need to simplify. And then I can tell that this has a power of 1, so what do I do with exponents that I am dividing? I subtract them. So 1 minus 1/3, actually it's 1/3 minus 1 equals -2/3. So that means it needs to stay on the bottom in the denominator. So as x approaches 0 of my function, 1 over x to the 2/3 power. And then from what I can see here, I know that I'm going to have, in this situation, in my limit situation right here, I know that I'm going to have a negative, or not a negative, an asymptote at x equals 0, which means that my derivative, remember this is all derivative, my derivative at x equals 0 is an asymptote, therefore it is not differentiable. Because in this situation, and if I wanted to look at a table, I would see that as x approaches 0, we will see that this equals infinity. So it would look something like this. My table, I want to plug in something really close to 0, like 0.00001, and I get a really big number. And if I plug in -0.0001, I see that I also get a big number. So it is approaching. So in the homework you'll have problems like this one. It says number 71, use the alternative form of a derivative to find the derivative at x equals c. So I'm going to use f prime of c, that's my alternative form, of the limit of f of x minus f of c all over x minus c as x approaches c. That's the formula I'm using. So I'm going to find the derivative at 2, since they tell me that c equals 2. So I'm going to take the limit of f of x. F of x is, I see right here, x squared minus 1. And then minus f of c. Well, if I plug in 2 in here, I get 2 squared minus 1, which is 3. So minus 3 all over x minus 2 as x approaches 2. And when I simplify that, I get the limit of x squared minus 4 over x minus 2 as x approaches 2. So then here, I know that I can simplify it even more. So that's x plus 2, x minus 2 over x minus 2 as x approaches 2. And I can cancel these out. So all I'm left with is the limit of x plus 2 as x approaches 2. So now I can use direct substitution, and when I do that, I get that my answer is 4. So the derivative at x equals 2 is 4. And remember that slope. So if I were to graph this, I know that the slope at my point 2 is going to be 4. And then another example, like number 78, we're still doing the same thing. It tells me to find the derivative at c, and in this case, c is equal to negative 3, using the alternative form, which is this formula right here. F prime of c is equal to the limit of f of x minus f of c over x minus c as x approaches c. And in this case, c is negative 3, so I'm finding the derivative at negative 3, which is equal to the limit of f of x, and f of x I know is going to be x plus 3 quantity raised to the 1/3, okay, minus f of c. Well, f of c is going to be f of negative 3, so I'm going to get negative 3 plus 3 raised to the 1/3 power. That's just 0 to the 1/3, which is 0, so minus 0 all over x minus a negative 3, which is going to be plus 3 as x approaches negative 3. And in this situation, I get what I got before. So I have x plus 3 raised to the 1/3 power over x plus 3 as x approaches negative 3. I cannot use direct substitution because I get a 0 on the bottom. However, I know that I have an exponent of 1 here. So 1/3 minus 1 equals negative 2/3, which means my power is going to stay in the denominator. So I have the limit of 1 over x plus 3 to the 2/3 power as x approaches negative 3. And I still cannot plug that in. But if I were to use a table of values, I would see that this won't exist. So this is not continuous. I'm going to have a vertical asymptote at x equals negative 3 right here in this situation, which tells me that it's not differentiable. So the derivative at x equals negative 3 does not exist.